All right, I'm going to start working through it up here. So do as much as you can by yourself. But if you get stuck, you can see what I'm working on. You do end up having to find the integral of cosecant, if I remember right. The antiderivative cosecant, which is one you can look up. So, well, we ran into it yesterday. You should have run into it yesterday. So. Oops. All right, there are other ways to simplify that, but okay. So we started off, it's of the form x squared minus 1, so we should be thinking secant squared, secant. So you do x equals secant, find the derivative of secant, multiply through by your dx here, so don't want to forget that. And we get to this point here, secant theta divided by tangent of theta. And then you're like, what do we do? If this was secant squared, that would have been nice. What would we have done if that was secant squared? We could do u sub with just u equals tangent, because the derivative of tangent is secant squared theta, d theta. We have that. But we don't have that. We don't have other squareds to work with. So what do you get? What's one option when you get to this point? You can always put it in terms of sines and cosines and hope things simplify, because all of the other trig functions are defined in terms of sines and cosines. So that's what I did. Okay, and that actually was just a fancy way of writing cosecant. So this is equal to cosecant right there. So the antiderivative of cosecant, it, like secant, is a really hard one to derive. We don't have to teach you guys how to do that. It's pretty crazy. And so that's one you just have to know or look up. Even mathematicians look up lots of antiderivatives. You can buy whole books. Well, they're not as popular now because now you can just look it up online. But they used to publish whole books, I mean, like really thick books that were just tables of antiderivatives. So they didn't do it for derivatives. Derivatives are so easy. I mean, you know a few rules, you can find the derivative of anything. But antiderivatives, it's much different. The back of your book has several pages of antiderivatives, and they're a lot like that. By the end of this course, you actually know everything you need to know to derive every single one of those in the back, except for just one or two. So in the back of your book. All right, a lot of them are trig subs. All right, so we look up cosecant. There's a couple different ways to write down the antiderivative of cosecant due to log rules and other ways that you simplify. Another way, so some of you may have written down the natural log of cosecant theta minus cotangent. So that also works. Both of those work. Okay. So where were we? So you get these cosecants and cotangents of theta, but what do we need to do? We need to get back in terms of x's. So I go back to my original substitution, x equals secant of theta. I rewrote it down here, so we didn't have to keep going back and forth. So x equals secant of theta, I thought of it as x over 1, drew my triangle, and I get theta. Secant is 1 over cosine, so cosine is adjacent over hypotenuse, so secant must be hypotenuse over adjacent. So so I know to put them x over 1, use the Pythagorean theorem, solve for this term, and then I use this triangle to find the cosecant and the cotangent. Cosecant is 1 over sine. Sine is opposite over hypotenuse. So I need a hypotenuse, which is x, over the opposite, which is that square root there. And similar with cotangent. Tangent is opposite over adjacent. So cotangent is adjacent over opposite. And so that's where I got that term. And don't forget the plus c. Questions about that?
So for the antiderivative of cosecant, is that something that we're at least expecting to memorize, or that we're sure on the test?
Yeah, we will try not to put that on the test for you. So, yeah. Secant's more likely to end up in cosecant, but yeah. I wouldn't put it on my test. So, I'm not solely writing the midterm, but yeah.
So I just got
How to get it when so I set up the triangle using this equation right here, my original substitution. So when I originally, way back early, I saw this, I recognized, hey, maybe I can do this as a trig sub. This x, if it was a secant, I would be good because I have an identity where I could turn that into a perfect square. I substituted x equals secant theta. So that's where I went back to make my triangle. Did that answer your question already? Okay. All right. Other questions? Okay. We're going to do a little experiment. I'm just going to cover this screen. I need to turn the lights off. So, Emily, do you want to come on up? You guys probably want to see the screen. Is it already on there? Okay. So, if you take the square here, that first one, that's one distance away. If you go twice as far, then that same amount of light spreads out over an area that's 4 times as large. So the same area here, it only gets 1/4 of the light, and then 1/9 the light. So that's where the inverse square law works. So we're going to do a problem with this inverse square light law. Okay, that's not a bad problem. Okay, so here's a street lamp. It's a tall street lamp. It's 5 meters high. Okay, and at the base of the street lamp, it measures 500 lux. Okay, I had to look up to see what a reasonable measurement would be. 500 lux is like the minimum standard retailers use to have in their stores. So when you're shopping in a store, that should be 500 lux. I measured in the last classroom that I had that had more lights than this. They asked me what the lux was in that classroom. When I was facing it up, it was like 650. So facing it like this away from the lights, it was like 180. So underneath this, right underneath the street lamp, 500 lux seems reasonable. All right. I care about a distance. I care about right underneath the street lamp to 5 meters away. And we're going to set it up this way. I'm going to call this distance x. So what is this distance? Oh, I gave you guys a big hint already. I tell you, we're really good at making you guys think that you know everything. So 25 minus x squared. All right. So what's the distance? Yep. See, I'm really good at making sure you guys know everything, and I don't know anything. I actually did that in my last class too, just later in the lecture, but I put it negative. So this is the hypotenuse. So you add the squares of the legs. So the distance for any point along that sidewalk, so any value along here, the distance that I am from the light is this term, right? So the inverse square law says the intensity of light given the distance is some constant that depends on your light source, how bright it is, divided by your distance squared. We can figure out what k is because we know one point right here. This should remind you now of what I'm going to do next. Should remind you of a spring problem. Okay, spring problems we make assumption about what the relationships are. If we know one point, we can figure out what our unknown constant is. Okay, so I know that the intensity of light is 500 when the distance is 25 plus 0 squared. It's 5. We already know it's 5. It's written on the... I already have that. So what do you get? You end up with a k over 25 times 500, and that goes to 12500 equals k. So our relationship is... Oops, jumping ahead here. The light, given any x, the light intensity, is that over the square root. Oops. Well, I guess I could put it there. It's the distance squared, but what's the distance? That's x squared. So we can't. Yep. That's the easy way to write. I was just making sure people see where that comes from. So now your job. So let me be clear about what this function tells us. If you give me an x coordinate, then I know exactly how much light intensity is hitting me, okay, or is hitting the sidewalk. Okay. So now your job with your neighbors is to calculate the average value of light from 0 to 5, the average light intensity of light on the sidewalk. Okay. So average light intensity. You might take a guess right now about what it might be. Write down your guess. See how close you are. So find the average. You guys probably want to see that. All right. So I want to know the average value over these 5 meters. Okay. So we do know some value. So this is a problem you should eventually be able to get a numerical value for, right? Something you can punch out on your calculator and get a decimal approximation for. So make sure you should think and see if that answer you got is reasonable in this context. Yeah.
Are you able to explain also how we get zero sometimes with some inverses? Because that confuses me. Where I've noticed in like some problems where I plug something into like an inverse, and somehow it leaves zero. But like I look at the unit circle, I'm like, how do you get that in its bounds?
Yeah. I'll talk about it in terms of the tangent that we get here.
Okay.
Inverse tangent. But yeah, if I don't fully answer it, catch me after class.
Yeah, no
I'll
worries.
explain some-
Thank you.
okay. All right, so I hear people talking about non-math stuff, which means like you guys are done and I've taken too long to do my problem. So here we go. No, that's good. That's good. How else do people in my class end up getting married if they don't have some time to just chat about other things? Like, all right. So here I set up the integral that we had before, just put it on a new page. My bounds are 0 to 5. Where did this 1/5 come from? Yep, 1 over b minus a of the integral of f of x. That's from our average value. That's how to calculate the average value of a function. So we're over 5 meters. We're spreading it over 5 meters. This is dividing by those 5 meters. And then I recognize that I need to do tangent. 5 times tangent. I'm picking tangent because I have something of the form back at to the identity tangent squared that connects tangent squared and secant squared. Tangent squared plus 1 equals secant squared. So the plus the constant gives it away about which identity I'm using. So, and I have to make it 5 tangent so that when I square the 5, I get 25. That way I can pull out a 25 and get my tangent squared theta plus 1. I have to have that tangent squared theta plus 1. It can't be plus something else for me to use my identity, and I can replace that whole thing with secant squared theta. Okay. I've got a 5 and a 25. Those simplify out to just a 5. And then dividing the 5 into the 2500, I end up with just 500. And the whole reason we did this was to hope that that denominator will simplify into something better, and we go from that sum to just a secant squared. The d theta, the dx is 5 secant squared theta d theta, and I end up with just a secant squared theta divided by secant squared theta, and it just goes to 1, just a d theta. So what's the antiderivative of 1? Okay? Yeah, so I've moved up from asking you what 1 plus 1 is to what's the antiderivative of 1. So at least we're still in calculus here. So you get 5 theta. You can do plus a c, but we're not worried about the c right now. So we're going to convert back to x's. So I do that with my triangle, with my original. Actually, I don't have to do it in this case because I don't have trig functions. I just have to go back and solve for theta. I don't have to figure out what the trig functions of theta are. So I go back to my original function, my original substitution here, and I solve x over 5 equals tangent of theta. And so I have to take the inverse tangent of both sides. Inverse tangent of x over 5 equals theta. And so that means my antiderivative here becomes 500 times inverse tangent of x over 5 going from x equals 0 to x equals 5. Okay? And I can substitute those in. At 5, I get 500 inverse tangent of 5 over 5, which is 1, minus inverse tangent of 0 over 5. Okay, so let's think about these. What does inverse tangent tell me? What does it tell me? What does it give me out? If I plug in a number, what does it give me out? It gives me out an angle. I give it a ratio of sides of a triangle. It gives me out an angle. So what angle can I... this tells me what I'm looking for is the angle I can take the tangent of and get 1. Yeah, so what angle can I take the tangent of and get 1? It's pi 4, so it's 45 degrees. That's when this is equal to this, because this is the opposite over hypotenuse. I mean, opposite over adjacent that the tangent is, so it's at 45 degrees. So this is pi 4ths. And inverse tangent of 0. So now I'm thinking, what angle can I take the tangent of and get 0? 0. You can also think about this in terms of the graph of tangent. Oops. Right? 0, 0 is a point on the tangent graph. That is a horrible tangent graph. So if I take the angle, the tangent of 0, then I get 0 out. So that's going to be 0. Okay? That's 0 degrees right there. So 0 radians. 0 radians. Yep.
If we use degrees, the answer wouldn't make sense, right?
That is exactly right. And that's exactly why we actually use radians. Degrees is not a distance. Radians is a distance. Like a radians is a measure, in this case, like meters. Radians is a physical distance. But degrees is not. So that's why we have to use radians. Okay, if you do degrees, then you have to like convert it, go to a circle, figure out what your radius is, and convert it, and you'll end up getting the radians. So anyway, so. So that's the other way to do this, right? In this case, it does seem easier in this problem. So instead of going all the way back to x's here, and plugging in x as 0 and 5, you could, when you had theta right here, you could go up and change your bounds using our equation. Using this equation, you could change your bounds and plug them in right there. So, yeah, that's probably easier in this case. And I'll even show you something that's even easier to begin with. So what was our average? Well, I mean, 125 pi, which is just a little less than 400. Yeah, so 500 pi over 4, which is about, what did you say, 392? Yeah, so that actually surprised me. I thought it would be less than that. Given the inverse square law and how fast light dissipates, I was expecting that to drop off a lot faster. I mean, if we're 500 here, we could actually plug in to figure out what it is at the other end. I can't remember what it is, like 280 or something. It's not that. We're going to do another example. It has to do with the we're not moving directly away from the light. So, like here, we're moving kind of sideways from the light, and so it has to do with that. So there is another way to do this problem. From the very beginning, I had a student do this, and maybe some of you tried this. From the very beginning, well, I didn't set it up quite as much in my last class. So I had students, instead of doing it in terms of x, they solved this distance in terms of theta right there. And now the hypotenuse, this in terms of theta, you know your opposite side, you know your adjacent side. Well, that means the tangent of theta is opposite over adjacent is x over 5. And now you can solve for x, because for any, here you're connecting your thetas with your x's. For any theta now, from 0 to what angle am I going to need to get all the way over here to 5? Pi fourths. So you can skip x's altogether if you think about this in terms of integrating with an angle instead of integrating across the sidewalk. So you can just go right to 1 over 5 tangent. Is it 5 tangent? Did I do this right? X is okay. I haven't thought through this all the way, obviously. It just happened in my last class. So anyway, you can think about it in terms of this angle and set it up just in terms of theta. And your bounds will be 0 to pi fourths. But I can't see now what I should be writing down over here. Okay. I'll think about that and I'll come back. Okay. So I told you that it actually kind of surprised me that that average was so high. So I did a little experiment. I said, what if I've got that same 5 meters? And I put a light source just 1 meter away. So now the distance on our, I'm going to call this 1 to 6. And here's our light source right here. And I get a light source that gives me the same measurement at this end, 500 lux. So if I'm standing under the light post or if I'm standing in front of that light, I get the same measurement, 500. But now, and then I said, I'm going to figure out what the average is across here. So I don't think we have time to find out the average. But what's the light intensity right here? Yeah. Yeah. We haven't had time to do the math, but for this situation, my light intensity given in x is 500 divided by x squared. because at x equals 1, I'm at 500. Last time at x equals 5, I was at 500. I had to change my k. But what happens if I'm at x equals 6? In this case, which is the same place as x equals 5 in the last situation. What's my light intensity? I don't know, what's that, like about 16 or something? It's like incredibly low. Yeah? I did move 5 meters, but I'm at a distance of 6. So 13.9. Yeah, so this is actually, x is actually the distance away from the light. And so I'm actually at 6 away. So it's really low, 13.9. So what I realized this morning as I was working on these problems, I realized why lights in stadiums are so stinking high. Okay. If you think of a football stadium, how high are those lights? Ridiculously high. I'm something like crazy high. You go to the Dixie State University Stadium, they're like so high. And I used to just think like, well, that gets them out of the way, right? Might be one reason. That's actually not the reason. So if you've got a football field here, and you tried to get the right intensity of light at the edge by lights that are nearby, what's the problem? It'll be nice here, but that light dissipates so fast that you're going to be really dark out in the middle. Because as you move, you're moving almost directly away from the light, and that inverse square dissipation law comes into effect. But if you put them really, really high, then as you move away, you're not getting that much further away. And so the light intensity doesn't drop off nearly as fast. So, and it helps you to keep the light intensity more, like we were looking at average values, helps to maintain a more even value where you don't have really bright spots and really, really dark spots. Which if you're a football player is important, because then otherwise you might turn around and you'd have a bright light there and you're like, where's the ball, coach? So anyway, that's what I learned today, doing some calculus, trying to prepare for this lesson. So hope you learned something too. Have a great weekend.
Thank you.
You're welcome.
Thank you.
No worries. See you guys.